So, we looked at the stability of retained austenite when you are heating to higher temperature using magnetic saturation method. So, we looked at the effect of temperature on the mass magnetization of the sample containing retained austenite. So, when the retained austenite containing sample is heated to higher temperatures, the retained austenite decomposes into ferromagnetic phases. For example, I showed you a graph which is shown in this slide, where the mass magnetization is actually measured as a function of temperature. So, if you increase the temperature, what happens? The retained austenite starts decomposing when the temperature reaches, for this case, for high silicon steel's case, that when the temperature goes beyond 300 degrees centigrade, you see a decomposition of retained austenite. This decomposition leading to a formation of a ferromagnetic ferrite, and then the transient carbides we will look at in earlier class. So, we look at in further. So, what happens in the heat affected zone and the fusion zones of wells when you apply a well thermal cycle. As I already explained, the temperature, the peak temperature across regions can change, can reach at varying degrees, starting from above melting point in the well center line to base material far away from the the temperature at room temperature at the base material far away from the well center line. So, in order to understand how the retained austenite fraction change along the well, heat affected zone as well as in the well zone. So, we will have to measure the magnetic saturations at varying points, right. So, for example, you have a well region, and this is well center line. So, as I always draw, now we need to understand as a function of distance from well center line how the retained austenite fraction can change, because that is going to determine the microstructure of the various regions from across the heat affected zone as well as the well zone. So, if you want to measure the magnetic saturation, we need to take the samples from the varying regions. For example, in the base material, in the subcritical heat affected zone, where temperature reaches below the critical intercritical temperature, and the samples at the intercritical regions, as well as the fine grained and the coarse grained heat affected zone. The disadvantage of the magnetic saturation method is when you are measuring retained austenite fraction, you need to have a significant amount of the volume of the sample measured in order to get reasonable magnetization measurements carried out on the sample. It is a bulk measurement. What do you mean by bulk measurement? You are measuring at the throughout the thickness of the sample. Okay, so in a bulk concentration, not as an, like for example, when you are doing an optical microscopy and look at retained austenite fraction, you are measuring very local regions, right. You are not measuring what is below the surface, you are just measuring on the surface. Whereas in the magnetic saturation method, you are measuring and throughout the sample in a bulk measurement. So, it is advantage, but the disadvantage is you need to measure over wide regions. See, for example, in this drawing, I have drawn circles where we machine the samples out and then do the magnetic saturation measurement. So, what happens here, suppose if this is your thermal profile after welding, for example, if I change the color. So, if this is my thermal profile after welding, so now if you imagine if the temperature is decreasing as a function of distance from well center line, and if you look at say for example this region, the temperature would vary to say 100 degrees or so. So, if you take a sample of, say in this case, if a seal thickness is say 3 millimeter, if you take 1 mm diameter sample from the well zone, along that 1 mm you may have a variation of 100 Kelvin. So, you are averaging the measurements over wide regions. That means that the effect is actually not really clearly delineated, the effect of peak temperatures, right. You are measuring the effect of a well thermal cycle where the peak temperature, say for example ranging from 800 to 900 degrees centigrade in one region. So, we need to measure it much more accurately with respect to the spatial distance. So if you want to have the effect of peak temperature on the retained austenite fraction, say for example we need to measure it with much finer resolutions, isn't it? Say for example when you measure at a given location, the temperature should not vary, say for example 5 kelvins. So if that is the case, then we will have to make the measurements at a very small area of the sample. Whereas in the magnetic measurements it is not possible, because we will have to machine out the sample with reasonable size in order to measure the bulk retained austenite concentration. It is very good to carry out measurements like in this graph. I showed you how to measure, how to study the effect of temperature on the retained austenite stability. So we can take a sample from the unwelded base material and then put it inside and heat it up to various temperatures and identify what temperature you see a change in magnetization, and that would give us how the retained austenite transforms to other phases while heating. And yeah, from that we can understand that what is the maximum temperature upon which retained austenite starts transforming to the other ferrite and the epsilon carbide phases. So in order to have a very refined fine measurements, so we will have to go for some other techniques to measure retained austenite. So one such technique which can be used to measure the retained austenite at a very local regions in the well zone is by using X-ray diffraction. Okay, so X-ray diffraction is another technique which can very effectively use to measure the phases that are the amount of phases that are present in the microstructure. The principle of X-ray diffraction I am not going to detail, but you can refer to some of the textbooks I referred in the beginning of the classes, beginning of this course. So the idea of X-ray diffraction is to get diffraction peaks of individual phases that are present in the microstructure. Say for example in trip steel we have two phases, right? So one is a BCC phase, which is ferrite and say for example in this case carbide free bainite, and FCC phase, which is retained austenite. So now what we are interested is the volume fraction of retained austenite present in the microstructure at a given location. So what do we do now? So we can carry out X-ray diffraction measurements at individual locations where the beam size of the X-ray diffraction can be as small as a few microns. So the gauge volume, the volume on which you measure the X-ray diffraction is very small compared to the measurements you do it in a magnetic saturation method. So in this case, because of the gauge volume is very fine, and we can measure in highly localized regions in the heat affected zone as well as in the well zone. So using the X-ray diffraction technique, we can precisely measure by the various ways I am going to explain in next slides. We can measure the amount of retained austenite present in the microstructure in the welded material. So the principle is very simple. So we get the diffraction patterns. So the intensity of the diffraction as a function of 2 theta. Okay, diffraction, that is then the angle between the incident and diffraction beam. So you can refer some of the textbooks which describe the X-ray diffraction. So right now we can assume, because it is too much for this course to explain about X-ray diffraction, so we can assume now we get the diffraction patterns of BCC and FCC phases that are present in the microstructure, and in our case in trip steel, so what we have is ferrite and carbide free bainite, which is also ferrite, and both of them are BCC, and then FCC, which is retained austenite. And these two phases would give you the diffraction patterns what you showed in this figure. For example, I put two diffraction patterns of high silicon and high aluminum steels and trip steel, which contain the mixtures of ferrite and retained austenite, BCC and FCC, and they would give you diffraction patterns at a given individual 2 theta, and the planes of FCC and BCC would diffract when they satisfy the Bragg's conditions, which is 2d sin theta is equal to n lambda. So lambda is the wavelength of X-ray when when the d spacings of the inter lambda spacings of the crystal planes, if they satisfy Bragg's law, for example, if it satisfies Bragg's law, and you will enter diffraction pattern. Okay, so for example, d is of 111, 110 of ferrite and austenite respectively, the austenite and ferrite respectively, would diffract in a given angle for a given wavelength of lambda, and then we record these diffraction patterns, and based on the intensities of these diffraction peaks, we can calculate precisely how much amount of austenite and ferrite present in the microstructure. Say for a typical BCC FCC mixture in the microstructure would give us a diffraction pattern what is shown over here in this graph, and we record the intensity versus 2 theta diffraction patterns, and then identify the peaks positions, and then from the peak positions we can precisely know what plane it is diffracting, because each plane have an defined d spacings, right. For example, if you know 2 theta, and then we can calculate for a given wavelength what is d spacings, and the d spacing, from the d spacings we can precisely see whether it corresponds to ferrite or austenite. So once we identify the planes of diffraction, and now we can see that what is the intensity, individual intensity of ferrite and the austenite. For example, in this case this is 200 austenite intensity, this is 200 ferrite intensity, and this is the peak, the first peak is a mixture of ferrite 100 and austenite 111, and generally we neglect that because it is very difficult to separate and this peak. So we would use the other peaks what you see over here, for example the austenite 200, ferrite 200, austenite 220, ferrite 211, and then austenite 311, 222, and then 220. So we can measure the intensities of individual ferrite and austenite peaks. So once you know the individual intensities, and we can combine it and then calculate a ratio which is shown over here. So the amount of retained austenite present in the microstructure is nothing but the total intensity in the diffraction, total intensity over the intensity of FCC peaks, right. So the total intensity over the intensity of FCC peaks, that will give us the ratio between the total microstructure over FCC, right. So that would again will give us the amount of retained austenite present in the microstructure. So this is very straightforward technique if you have a good equipment. So we can measure the entire diffraction pattern, the intensities of all the diffraction peaks over the intensity of FCC peaks, and of course we have various factors, the multiplication factor and other factors, and that no need to worry about it. So basically this equation is very simple. So we have a total intensity, for example this is total ferrite intensity and this is total austenite intensity, and combined together it will give you total intensity of the microstructure, diffraction intensity of microstructure over basically the intensity of FCC peaks, that will give you the volume fraction of retained austenite in the microstructure. Similarly, you can also calculate the lattice parameter of the individual FCC and BCC, which we may not need unless you need to calculate the strain, residual stress in the microstructure, which is not needed for this course. So we can measure from the diffraction patterns which I showed you in the previous slide, by measuring the intensities of the ferrite and austenite peaks, by calculating the ratio of total intensity over the intensity FCC peak, we can calculate amount of retained austenite present in the microstructure. Okay. So now what will happen in the well zone? So we can measure over the regions in the welded trip steel, for example. We can start from the base material far away from the well zone, and I am showing you a graph describing the retained austenite variation along the distance from the well center line. Okay, so well center is over here, so that is over here, and this weld was made in high silicon steel, containing silicon containing trypsil using GMAW bead on plate weld, which I showed you in previous lectures, and you can refer the figures and then identify. Now you can look at the weld zone regions in the slides which I showed you in earlier videos. So now if you look at the retained austenite variation along these lines, it's very interesting to see it, right? It is symmetric. If you look at it along the weld center line from this side and this side, it looks very symmetric, but we will see one by one. So we are measuring it very small regions, individual points over here. It shows individual measurements of X-ray diffraction, and for measuring this graph we used a very high energy X-rays which is known as synchrotron X-ray. Sorry. Synchrotron X-ray, which are very high energy X-rays and which can penetrate at, say, for example, in this case 3 millimeter thick plate. So we can measure the diffraction the other side of the sample, which is known as transmission X-ray diffraction. In laboratory scale we will be doing it only in reflection mode, but because we use very high energy X-rays which can penetrate the sample on the weld and can come out on the other side, and we measure the diffraction on the other side in transmission. And due to that, these measurements are done. For example, you have an sample and the beam comes here and then diffraction happens. Okay, so this is for example the angle between incident and diffracted beam. So if we measure the diffraction on the other side of the sample because it happens in the transmission. Okay, so we can measure precisely by controlling the beam size and the location, and we can measure the retained austenite along the thickness of the sample for a given region. So if you look at this graph is made with various points. For example, if you move far away from the weld center line, about 15 mm from the weld center line, so 15 mm from the weld center line, you see that you are in the base material. So the retained austenite fraction is about, say in this case, 11%, right? And then if you are moving close to the towards the weld center line, what happens? Nothing happens until to some temperature, some regions. Okay, say for example until you go about 11 mm or so from the weld center line. So then you see that there is a decreasing in retained austenite fraction. So retained austenite starts to decrease, say if you go about 11 mm from the weld center line. And if you look at the temperature, for your reference, I also given here the temperature cycle or peak temperature reached during welding when we on the plate on which we measure the X-ray diffraction. Say temperature at this region. Okay, so for example, the region around say 10 mm from the weld center line, it goes around. So in this case, it goes around say 500 degrees centigrade. Okay, say over here, isn't it? Say at this temperature at this region, say 11 mm for example, 11 mm is somewhere over here. Okay, so if you extend this, so this goes to about 500 degrees centigrade. So in this case, we already clearly see that when a temperature increase to say 500 to 550 degrees centigrade at 10 mm, you see a decrease, the austenite start decomposing into various phases. Okay, and in the magnetic saturation measurement, we looked at the temperature at which retained austenite transforms to somewhere around 300 degrees centigrade, because here we see that in real case it's about 500 degrees centigrade, because the heating rate in weld is very high. So you may have to increase the temperature much further, so that the kinetics can lead to increasing in the decomposition rate. Whereas in the magnetic saturation measurement, we heat it very slowly. Okay, so you can see the effect of heating rate already on the decomposition mechanism of retained austenite. So what happens here in this case? So moment the temperature goes around 500 degrees centigrade, the retained austenite fraction start to decrease. That means that, so recall from the magnetic measurements, the retained austenites is transforming into and ferrite and the other carbide mixture. So the austenite would start transforming into first epsilon carbide and eta carbide and subsequently cementite, right. So you see that when the temperature is going above 500 degrees centigrade in the well zone, the retained austenite decreases continuously at this point, okay, somewhere over here around 650 to 700 degrees centigrade, you reach the minimum value. Okay, so the value of retained austenite is almost close to 0. So that means that we have not nucleated new austenite. So new austenite nucleates when the temperature goes above your A1 temperature, right. Okay, so this is the temperature at which you start nucleating new austenite when you are heating up. Okay, so now if the temperature is below the A1 temperature, what will happen? Only the retained austenite present in the microstructure starts decomposing, okay, and this decomposition would lead to the formation of ferrite and cementite in retained austenite. And when the temperature is just below the A1 temperature, say somewhere around 650 to 700 degrees centigrade, all the austenite in the microstructure are completely decomposing. Okay, that's what it shows over here. The austenite fraction decreases to close to 0%, and then if you move further close to the fusion zone, the austenite fraction starts to increase. That means that we are reaching the intercritical temperature region. The peak temperature during welding goes above, say in this case 700 degrees centigrade. That means that you are nucleating new austenite. Okay, you are reaching to the intercritical temperature region. So then what happened? Then intercritical temperature region. So moment your temperature reaches the intercritical region, there will be local partitioning of carbon, right. As I already explained when I was explaining you the trip steel heat treatment, the moment the temperature reaches to intercritical temperature, the sample, the austenite in the sample would start get enriched in carbon because of the partitioning of carbon between the coexisting ferrite and austenite. This is C alpha line and C gamma line, right. So the moment your temperature goes to intercritical temperature, your austenite would start get enriched in carbon. That means that the stability of austenite increases. Okay. Subsequently, when you cool back to room temperature, this retained austenite can be stable. Okay. Whereas in the temperature below this temperature, A1 temperature, austenite is not nucleating. Okay, so what happens then? Austenite is not nucleating. That means that austenite, whatever present in the retained austenite, will decompose completely and will lead to almost 0% retained austenite in the regions where the temperature is below A1 temperature. So when you go above A1, you will reach to the intercritical temperature region, where you will have an ideal temperature at which you have a maximum partitioning. That is similar to heat treatment. We have seen in a conventional trip steel heat treatment, where the temperature would be in the intercritical temperature regions, and whereas say for example in this case somewhere around 900 to 1000 degrees centigrade, when the peak temperature reached, so you should also be careful here. We are not welding in equilibrium condition, right. So we are heating up extremely rapid case. So the entire temperature, the phase diagram would shift above. So you would form an A1 temperature if it is 800 degrees centigrade in conventional case. In this case it may be different because it is not equilibrium case, but the principle, the fundamentals are the same. Okay, so at this temperature, when at this location you reach the ideal volume fraction of both ferrite and austenite, can lead to a maximum stabilization due to the intercritical annealing, right, where two phases are coexisting. So you will reach the maximum temperature, maximum volume fraction at this location, which is roughly say around -6 mm from well center line, and this can change. Suppose if you are heating up very fast in laser beam welding, for example, then this region would change, it will shrink, okay, the entire regions. So in this, because again the temperature gradients are much different, okay, but it will have a similar pattern. Okay, and when the temperature reaches an intercritical temperature, where both ferrite and austenite is coexisting, and you will have an optimum partitioning of carbon to the austenite can lead to the increasing fraction. So, if you further move above for example, A1 temperature, what will happen? A3 temperature, you will have a single phase austenitic microstructure, and then again there is no partitioning, right. So, there is no partitioning, that means that it will decrease continuously when you reach a fully austenitic microstructure. And if you move close to the fusion boundary, then again it will increase the austenite fraction. Why? Because the carbon can also migrate from the well zone when it is solidifying, and carbon can also migrate to the adjoining austenitic microstructure, because when delta ferrite nucleates at the fusion boundary, delta ferrite sends the carbon because of the low solubility of carbon in delta ferrite, and this can also send carbon to the well central line as well as towards the austenitic region in the heat affected zone, the coarse grain heat affected zone, and due to that carbon can enrich the stability of retained austenite in the fully austenitic regions, thereby the austenite fraction increases again, and subsequently you will have enrichment leading to increasing austenite fraction at the fusion boundary. So, if you look at this graph, the lesson what you will have to learn is even though you have uniform temperature gradient, based on the peak temperature reached, you will also change the microstructure significantly. In a conventional ferritic steel, ferritic palladic steel, this effect is not significant. Why? Because there is no retained austenite in the microstructure. Okay, but because of the presence of retained austenite, you see you have the effect of the peak well thermal cycle, in this case until 15 millimeter from the well central line. Okay. Whereas in the conventional steel you will not see any effect until when you reach above A1 temperature, where you will have a microstructure changing to austenite during heating, and subsequently it will transform to martensite or very other low temperature products. So, because of the presence of retained austenite, we enlarge the heat affected zone. So, remember what is definition of heat affected zone. So, when you see the when you can measure the effect of peak temperature in the microstructure, the effect of peak temperature in the microstructure, if any noticeable effect is seen, then that is what heat affected zone. Now, we already see a noticeable effect until in this case around 11 to 12 mm from the well central line. That means that we enlarge the heat affected zone to much larger distances compared to ferritic palladic steel. Okay. And you should always be careful when you have retained austenite in the microstructure, your heat affected zone will be really broader, and the peak temperature reached during welding would determine the stability of retained austenite, as I already explained using this graph. So, in this is in the case of high silicon steel and high aluminum steels, you will see the similar effect. Only thing is the stability of retained austenite is much lower in high aluminum steel than the high silicon steel. So, you see again the effect until say until 11 millimeter or so, you see no effect, and then subsequently it decreases, okay, until you reaches the peak temperature reaches to the A1 temperature. Once the A1 temperature reached, you will have the intercritical regions leading to partitioning of carbon, and resulting in increasing in volume fraction of retained austenite, and subsequently when you go towards the fusion boundary, obviously you reach the single phase austenitic region, and that will lead to a decreasing austenite fraction. Okay. In a high silicon steel, we also saw the austenite fraction is increasing when you are moving to the fusion boundary, whereas in aluminum steel does not show that effect, mainly because of delta ferrite formation. Okay. So, the formation of delta ferrite can establish some delta ferrite leading to a decreasing in retained austenite fraction. Okay. And because you have only retained delta ferrite stabilizing at this temperature because of the aluminum partitioning, which I already explained in my previous videos. So, you have a continuous decreasing in retained austenite fraction, and then of course in fusion zone you do not have any intercritical treatment or any other phase transformations other than complete monazite transformation, whereas in these regions the peak temperature would change the austenite formation and the decomposition mechanism. So even though you have a similar microstructure in the base material in both high silicon and aluminum steel, and you may end up getting different volume fraction of phases in the heat affected zone. So it's always be very careful when you are welding a multi-phase microstructure, especially if retained austenite is present in the microstructure. The volume fraction of retained austenite can change as a function of peak temperature reached during welding. So I already explained the effect of peak temperatures when the peak temperature is less than the A1 temperature. A1 temperature is the maximum temperature upon which you nucleate new austenite while heating, and if it is less than that temperature, whatever retained austenite present in the microstructure would decompose, okay, based on the peak temperatures again. When the temperature is just below A1 temperature, you decompose all retained austenite to mixtures of ferrite and carbides. And the moment you go to the intercritical temperature above A1, so you will end up having a partitioning of carbon between the coexisting ferrite and austenite, and that can lead to increasing austenite fraction in the intercritical region. Subsequently, when your temperature goes above A3 temperature, where you have a fully austenitic microstructure, there is no partitioning. So you just cool down whatever temperature at the fully austenitic region. Based on the carbon concentration of that region, you would end up getting retained austenite. There won't be any enrichment. Subsequently, when you are moving to the fission boundary, either in high silicon steel, aluminum steel, and high silicon steel, there is a partitioning of carbon, whereas in high aluminum steel and diffusion boundary you have a stabilization of delta ferrite, the fraction decreasing retained austenite fraction. So I hope it is clear for you how the retained austenite changes along the well zone, starting from base material to the center line. Based on the peak temperatures, we can have varying amount of retained austenite fraction. The other lesson I want to give you here is, if you have metastable phases like retained austenite in the microstructure, you will also enlarge the heat affected zone. You can conventionally, you won't see any effect if you have ferritic pelletic steel, noticeable effect until you peak temperature reaches close to A1 temperature, and you will see maybe some sort of very small effect which is not noticeable in terms of the properties as well as the microstructure. But if you have metastable phases like martensite or retained austenite, and you will see the effect significantly, thereby you can say that the heat affected zone is enlarged in this kind of steels due to the change in microstructures you observe as a function of peak temperatures. And you can also see the effect very clearly in the mechanical properties, the effect of retained austenite fraction. And you see that whenever the regions at which the temperature reaches to close to just below A1 temperature, where you don't nucleate, where you have a minimal amount of retained austenite, right? So when you have a very minimal amount of retained austenite, for example, around in previous graph I showed you. So in the regions where 0% retained austenite is there, close to 0%, say -6 to -8. Okay, where the temperature reaches just below A1 temperature, you see extreme softening. So this is the hardness as a function of weld center line. So this is our weld center line. So whenever the peak temperature it reaches just below A1 temperature, where we have a minimal retained austenite, you see material softens significantly. Okay, when the base material hardness is about 340 Vickers, in these regions where the austenite fraction is nil, the hardness decreases to 260. Why? Because the retained austenite is transforming into soft ferrite and carbide mixture, leading to decreasing in hardness. Okay, in the regions where we have a 0%, close to 0% retained austenite, we have extreme softening, and this effect is seen in both the cases. In high silicon steel is very significant because the effect is also very significant. In high aluminum steel's overall retained austenite stability is very poor, and you will have extreme softening. Of course, in the well zone, you will have its own retained austenite fraction, as well as based on the segregation microstructure, you will have very high peak hardness. So we will conclude here with this, in the trip steel. And we can also look at the same effect in dual phase steel as well. And dual phase steel, instead of austenite, we have martensite in ferrite matrix, right. So, like in austenite is decomposing to ferrite and cementite mixture, the martensite in the microstructure would also temper. So, the effect too is also similar. When martensite is there, martensite will also temper, and then will the martensite would again transform to the mixture of ferrite and cementite, okay, in the same way where the austenite would transform to as I explained, to ferrite and cementite mixture. Your martensite would also transform into ferrite and the carbide mixtures in the same manner, and due to that you will also see the effect similar to what you see in the trip steel, where when the temperature is just below A1 temperature, you will have a significant transformation of austenite into soft ferrite and cementite, and that will lead to the transformation the tempering of martensite leading to a softening. What I show over here is in two cases, one is in laser beam welding and the other one is a plasma welding. In both the cases, especially in plasma welding, you will see the effect is very significant, the significant amount of softening you would observe, and because of the tempering of martensite, when the peak temperature reaches is below A1 temperature, and that will lead to the softening in the heat affected zone where the peak temperature reaches below A1 temperature, and you can see the effect. Only thing is the effect is not significant because of very narrow temperature region, narrow weld region. So with this we will conclude the retained austenite fraction. So we looked at two techniques. The one is the magnetic saturation method to measure the retained austenite fraction, and it is a bulk measurements, and it can give the information about retained austenite over wide area. So we have to find out, we have to use other techniques where we can measure retained austenite very locally, with very good spatial resolution. So we can use X-ray diffraction, and I explained using X-ray diffraction how the retained austenite fraction changes over the weld regions from base material to the weld central line, and based on the peak temperature reached, and we also saw the retained austenite fraction can also change, whether it completely decomposes to a mixture of ferrite and austenite, ferrite and cementite, or when the temperature reaches to intercritical temperature wherein both ferrite and austenite coexist, then you will have local partitioning which leads to the transformation of retained austenite, the stabilization of retained austenite at room temperature, and when the temperature reaches to fully austenitic region, there won't be any partitioning. So based on the carbon concentration at that region, and you will have low retained austenite compared to the intercritical regions. Okay, thank you.